Have you ever wondered what everything is made of? I mean, everything. The phone in your hand, the air you're breathing, the stars in the sky. Well, it all boils down to a surprisingly short list of ingredients. Today, we're diving deep into the most fundamental building block of them all, the atom.
So here's our game plan. First, we're going to take a quick trip through history to see how our picture of the atom has totally changed over time. Then, we'll get up close and personal with the particles that make up an atom. After that, we get to the really cool part, the rules that govern all of chemistry, which we're calling electron real estate. And finally, we'll pull it all together with the ultimate cheat sheet for understanding matter.
Okay, first up, picturing the atom. You know, our idea of what an atom actually looks like has been on an absolutely wild ride. It went from a simple little ball to something, well, something that's almost impossible to picture.
Just look at this timeline. We started out thinking atoms were basically tiny, indestructible billiard balls. Then, for a while, the best model we had was a plum pudding. Seriously. That quickly got upgraded to a mini solar system, which then got completely thrown out for our modern view, a bizarre, fuzzy cloud of probability. So how in the world did we get from A to B?
So let's go back to 1904. The top theory was this plum pudding idea. Just picture a blob of positively charged stuff, that's the pudding, and stuck inside it are these little negatively charged electrons, like plums. It's simple, it's straightforward, and it was about to be proven completely wrong by one of the most famous experiments in history.
And here it is. This is the experiment that changed everything. Ernest Rutherford's team was shooting tiny alpha particles at a super thin sheet of gold foil. Now, if the plum pudding model was right, those particles should have sailed straight through. But they didn't. To everyone's complete shock, some of them bounced right back, as if they'd hit a solid wall. That could only mean one thing. The atom wasn't a soft blob. It had to have a tiny, super dense positive center. And just like that, the nucleus was discovered.
Fast forward a bit, and all these discoveries lead us to the quantum model. And this is where your brain might start to hurt a little. Forget those nice, neat orbits like planets around the sun. It turns out we can't ever know exactly where an electron is. All we can do is to find a region of space, this electron cloud, and say, okay, there's a 90% chance of finding the electron somewhere in here. Weird, right?
So we've got this tiny, dense nucleus sitting inside a big, fuzzy cloud. But what are these things actually made of? Well, that brings us to our next section, the atom's ingredients. Turns out, for all its complexity, you only need 3 tiny particles. In the center, in that nucleus, you've got your positive protons and your neutral neutrons. These are the heavyweights. They make up pretty much all of the atom's mass. Then, whipping around the outside in that cloud are the super light negative electrons. Their mass is practically zero, but as we're about to see, they run the whole show.
Now here's the most important rule of the game. An atom's identity, what makes it gold instead of lead, is determined by just one thing, the number of protons it has. That's its atomic number. Take a look at copper here. It has 29 protons. It will always have 29 protons. If it had 30, it wouldn't be copper anymore. It'd be zinc. Now the number of neutrons can change. That just gives you a different version or an isotope of that same element.
Okay, we've met the players. Now we get to the real secret sauce of chemistry. Why is sodium so explosive in water, while the neon in a sign does absolutely nothing? It all comes down to how those electrons are arranged. So let's talk about electron real estate.
Okay, the official term for this is electron configuration. It's the specific address of every single electron sorted by energy levels, then sublevels, and finally orbitals. I know, that sounds super complicated and a little intimidating. But don't worry, there's a much, much easier way to think about this.
Let's just think of it like a hotel. The atom is the building, the energy levels are the floors, and the orbitals on each floor are the rooms. Now, electrons are kind of like lazy tenants. They always want the room on the lowest possible floor because it takes the least amount of energy to live there. And every tenant in this hotel has to follow 3 simple house rules. First, the Aufbau principle. You have to fill the bottom floors first. No one gets to move into the penthouse until the lobby level is full. Second, the Pauli exclusion principle. Only 2 tenants per room, and they have to have opposite spins. Just think of it like they have to sleep head to toe. And finally, Hund's rule. If a floor has multiple empty rooms, everyone gets their own private room before anyone has to get a roommate. Simple, right?
So why do we care about this weird electron hotel and its rules? Because of this one central idea. This is the key to all of chemistry. The personality of an element, how it behaves, who it bonds with, whether it's reactive or stable, is completely decided by how its outermost electrons are organized. That's it. That's the whole game.
Now that sounds like a lot of rules to keep in your head. But what if I told you there was a tool, a master key, that has all of this information built right into its very shape? Well, there is. Let's talk about the ultimate cheat sheet in science.
And here's the best news you're going to hear all day. You do not need to memorize all those complicated electron configurations. Why? Because the periodic table is designed specifically so you don't have to. That weird shape it has, it's not random at all. It's a perfect visual map of the electron hotel and all its rules.
And because it's organized that way, these incredible patterns just emerge. We call them periodic trends. Take atomic size, for instance. As you go down a column on the table, you're adding more floors to our hotel, so naturally, the atom gets bigger. But as you move across a row, you're adding more protons to the nucleus, which pull all the floors in tighter, so the atom actually gets smaller. And size is just one of many things the table tells us at a glance.
What this means is you can basically read the table like a map. You want to find the biggest atom? Just head to the bottom left corner. You want to find the element that's the absolute best at ripping electrons away from other atoms? Head to the top right. The answers are literally built into the layout. It's an incredible piece of design.
And this is where it all comes together. Why do elements in the same column act like a family? Why are they so similar in their behavior? It's because they have the exact same number of electrons in their outermost shell. Their electron real estate looks the same on the outside, so of course they have similar chemical personalities. The rules of the atom literally create the structure of the table. See? It all connects.
So, there you have it. From a simple little sphere to a fuzzy cloud of probability, we've built a map that predicts the behavior of all 118 known ingredients of our universe. It's an amazing, predictable pattern. And that leaves us with one last, really fun question. Based on all these rules, what do you think element 119 will be like when we finally make it? The amazing part is, the table can already give us a pretty good idea.